Welcome to this afternoon session. Pleased to welcome our first speaker, Jeremy Mann, who's going to talk about the AdS antibody problem at large spin. Please.
Thank you very much, and thank you to the organizers for the great conference and for the opportunity to present my work with Peter Kravchuk, based on our paper from last December and some further work in progress. So let me start by introducing what the problem is. So we're in a unitary and local QFT in AdS, and we're specifically interested in the lowest energy n particle states at fixed spin. So the goal is to compute the spectrum of the so-called twist E prime in the large spin limit. So how is this tractable? The idea is to first think about the case without interactions. Then these particles will go into these orbits bound by the AdS radius, and the spectrum will just be a simple spectrum with a gap and a degeneracy of the ground state that grows, starts growing with the spin from 3 particles onwards. And if we imagine introducing a small perturbation that's much smaller than the original energy gap, then this will lift the degeneracy in a controlled way that should take the form of an n-body problem on this degenerate subspace. So how do we make a small perturbation? There's the obvious way of just introducing weakly coupled interactions, and there's the more interesting way in this talk, which is ensuring somehow that all of these particles are well separated. And in AdS, one way this can happen is at large spin, because, for example, 2 particles, their distance at large spin grows like log j in units of the AdS radius. So this is the idea. And the main results of this talk, which I'll try to explain, is that most of the large spin spectrum in this model, in generic AdS models, is described by quantum mechanics, where the Planck's constant is inverse spin. And this quantum mechanics, I'll explain it explicitly below. So this is the result, but my motivation to study it is this broad framework of coarse holography. And the idea is that I can take any unitary conformal field theory, and if I look at some light cone limits of its correlation function, then it will be dual to a large distance, low energy effective field theory in AdS. And if I impose crossing in this limit, crossing symmetry, this will instate locality of interactions in this putative effective field theory. Now, this framework has not been explicitly developed yet, even though it's an interesting analytic corner of any CFT, presumably. And so the case study of this talk is a subset of operators of primaries that appear in these light cone limits called multi-twist. And the fact that their anomalous dimension should correspond to those of these multi-particle states at low twists that I mentioned before. And the conjecture I'll make is that this same AdS n-body problem at large spin appears in the spectrum of anomalous dimensions of multi-twist primaries in these conformal field theories. And I'll provide some evidence in the form of studying crossing of these correlation functions in CFT. Okay, so the plan is to first introduce the space of states on which the n-body problem takes place, then add some interactions at weak coupling that lifts the degeneracy, and study the corresponding quantum mechanical problem explicitly. Then I'll show why the large spin expansion is semi-classical and compare explicit finite spin data with semi-classical approximations. And finally, I'll try to explain how this semi-classical system appears in general CFTs. So let me start with the states. In free theory, just a free scalar, charge scalar phi, whose mass squared is related to the boundary dimension delta phi. And I'm interested in the lowest energy states. So I'm minimizing twist at fixed spin. The minimum is n times delta phi, and it's reached when transverse spin is 0. And if I plug these in numbers into my Ward identities for the AdS group, I obtain that the wave function of these states is completely determined by a holomorphic function of variables alpha on the unit disk. So this alpha is, its phase is given by the angle of rotation phi of these particles, which take these helical trajectories, minus the global time. And the norm of this alpha is proportional to the tangent of the AdS global radial coordinate. So my lowest energy states can be seen as wave functions in the tensor product of holomorphic L2 functions on the disk, with a measure that comes from that of free fields in AdS, which takes a simple form. And for the large spin limits, it will be useful to see these alpha coordinates also as phase space coordinates, in the sense that if I take this disk on which alpha lives and see it as a Kähler manifold, a symplectic manifold, then this holomorphic L2 space is the quantization of this phase space, where h bar is inverse delta phi. So while this h bar will remain finite, it'll be useful to think of alpha roughly as a phase space or a fuzzy disk. Now, the last thing I have to do to get irreducible representations of my isometry group is add a lowest weight condition, which translates to, on these holomorphic functions, to translation invariance and homogeneity of degree j. Since j is an integer, this means that I have a finite dimensional Hilbert space of lowest weight states that grows like j to the n minus 2. And this is the arena of my n-body problem. So now I want to introduce some interactions that will lift the degeneracy in this subspace. So the simplest but representative interaction would just be this Yukawa interaction mediated by a scalar sigma. And since I'm only interested in the spectrum of phis, I can integrate out this sigma field and get this phi-4 interaction mediated by the bulk-to-bulk propagator of sigma. Now, at weak coupling, the leading correction to the energy levels is just given by degenerate perturbation theory, such that the matrix elements of this energy correction are the matrix elements of this potential. And since my lowest energy states are very symmetric, they only depend on one variable alpha in AdS, I can integrate out the transverse degrees of freedom and obtain matrix elements on this L2 Hilbert space. So in other words, the matrix elements of my n-body problem are given by this effective potential Un, which is simply related to for a sum of pair potentials, where each pair potential is just a 4 points exchange diagram, but localized in the alpha coordinates. So you can compute it explicitly. We did this. It's a function. It's only a function of the hyperbolic distance between these points, and it emits a nice large distance expansion, a power series expansion, whose leading power is controlled by delta sigma and takes this form. So you see that it's suppressed when the particles are near the boundary and well separated. So now we have an explicit Hamiltonian on this finite dimensional Hilbert space, so we can do numerics. So one example here of a sample spectrum at n equals 4 and j up to 120 looks like this. And what I want to emphasize is that most states accumulate near this ground state here. And by most, I mean that the remaining states are just a vanishing fraction of the overall dimension as j tends to infinity. And what you can check about this, these states here that accumulate near the ground states is that their wave functions are well supported in these configurations where particles are near the boundary and where everything is well separated, so where this picture of the introduction applies. this second accumulation point, which is separated by a gap, fits with what would look like a three-body problem, but where one of the bodies is a composite of two bodies leading to an energy gap. And if you can think of these higher trajectories as corresponding to two-body problems of two or three-body composites. So this is what these spectra look like. And I want to explain how to approximate this part by a semi-classical system. So to do this, I'll use this framework of Berzin-Toeplitz quantization. And for the purposes of this talk, you should just see it as a machine which spits out a semi-classical expansion. This machine needs three ingredients: a space of holomorphic functions on complex projective space, a measure on CPN, which defines a scalar product, and that has the following large spin asymptotics. And finally, a Hamiltonian in the form of a Toeplitz operator. What this means is that it acts on wave functions by first multiplying by a potential or a symbol uj, which is non-holomorphic, and then orthogonally projecting back to holomorphic wave functions using this scalar product. And the claim, or the result of this framework, is that the large spin limit is semi-classical, the phase space is Kähler, the Kähler potential is the exponential decay of this measure, and the Hamiltonian is given by the leading asymptotics of this symbol uj. So to fit this framework, we had to do a little trick. We needed to go to what we call momentum space. This is a different realization of our wave functions, and we call it momentum space because it realizes alpha derivatives as a multiplication operator in the argument z, and it maps the translation invariance of lowest weight states to momentum conservation in matrix elements. But it's not a literal Fourier transform. It still maps a space of polynomials to a space of polynomials, and we ultimately get holomorphic L2 functions on the complex plane. Okay, so this is the method. From after doing this translation, you can construct this measure and this Toeplitz operator. And the result is as follows. We find a phase space given by the positive Grassmannian, quotiented by the cyclic group, and the Kähler potential and the Hamiltonian take a simple form in terms of these momenta. Now, there's a nice way to understand this, these results, harking back to this interpretation of alpha as phase space coordinates. You can think of the large spin limits as pushing these particles to the boundary. And if you think of this unit disk via stereographic projection as the unit time-like hyperboloid, then it corresponds to degenerating this hyperboloid into the forward light cone, which is parametrized in terms of these momenta by the height and angle of this light cone being the norm and angle of the momenta. And if you plug in this expansion into the original potential we had in the tree level n-body problem, you indeed find this function as the leading power. Finally, in the positive Grassmannian, it's defined by the requirements that this denominator, which is a Plücker coordinates, is positive definite. And the Zn is just the cyclic permutations of my points. So this is my classical limit. And while this Hamiltonian may look unusual, it takes a very simple form. It has a unique global minimum corresponding to the configuration where these momenta have equal length, and they form a regular polygon on the circle. And it grows in all directions until it reaches the boundary of the Grassmannian, where it diverges. So these go to 0. That happens either when angles align or when one of these light cones shrink to 0. Okay, so now we have an explicit Hamiltonian. We can do semi-classics. And So for example, we can relate the integrated density of states, number of states below a certain energy, to the symplectic volume. And here you see that taking the same data I showed you before, there's a nice convergence, linear convergence to the symplectic volume for most of the states. Similarly, since there's a unique minimum, very simple structure, we can approximate the lowest states by a harmonic oscillator with calculable frequencies and h bar squared corrections. And this indeed fits the data of the lowest lying states. Okay, so that's all I have to say about the semi-classical approximation to this n-body problem. Now let me explain or sketch how this can be embedded in conformal field theory. The idea is to put my CFT on the Lorentzian cylinder, time times a d-1 sphere, and employ the Weyl transformation that Alde and Maldacena used in a similar context, which creates an AdS3 and an AdS radius out of transverse directions. So you should think of the boundary of this AdS3 as corresponding to the equator of this SD-1. And I can introduce this same alpha variable here and think of limits in this alpha variable in the same way as an AdS. And finally, I do a Wick rotation at fixed alpha, which has the effect that now Euclidean time evolution is generated by twist instead of energy. So large Euclidean time will suppress twist. And now my claim is that if I look at this two endpoint function in these coordinates, then the limits where the alphas go to the unit disk and the limits of large Euclidean time will be light cone limits that will, inside of OPEs, describe large spin, low energy states and their spectrum. So to do this, I have to study crossing of this correlation function in two channels. The first is the charge neutral channel, where if I take OPEs of equal alpha states, of equal alpha fields, I find that the light cone limit suppresses energy or twist independent of spin, with leading exchanges given by the identity, so just two-point functions, and then leading twist exchanges, like, for example, sigma in this holographic model. So these are just calculable four-point functions. On the other hand, in the charge n channel, where I take OPEs between fields of the same charge, I obtain the, so I want to think of this channel as these phis acting on the vacuum at large Euclidean time evolution. So this should be like a low, this is like a low temperature limit, which projects onto the lowest twist states, which will appear in this OPE. And when the dust settles, we find that we can understand these phi fields in this limit acting on the vacuum as coherent states on this holomorphic L2 Hilbert space. And the matrix elements of the anomalous dimension of these multi-twist primaries corresponding to the same large distance potential as in my AdS n-body problem. Now, of course, this only applies in the limits where these points are near the disk. So to invert this into a solution for the spectrum, I have to assume that the states I'm considering are indeed supported in these well-separated configurations, as we saw in the weak coupling problem. So let me finish with a selection of future directions. Apart from sort of proving that this semi-classical problem describes these multi-twist operators in general CFTs, it would be interesting to push this idea of coarse holography and more specifically reformulate this light cone bootstrap program as a large spin or large distance and low energy EFT in AdS. And a good way to perhaps find information on this would be to compare with planar gauge theory, where there's results in this direction, and compare with the near threshold expansion of the S matrix, which is the flat space analog of this EFT. And finally, an interesting regime which goes to the boundary of validity of this EFT but still makes contact with some analytic formulations like the superfluid, would be to look at large N, and in particular, making analogies with the fractional quantum Hall effect, which has similar N-body problems. It's when N squared scales like J that we expect perhaps some non-trivial phases to appear. So with that, I'm done. Thank you very much.
We have time for a few questions.
Thank you for the very nice talk first. You said something about a momentum space transform that is not actually a momentum space transform. Can you say something about this? What is this, like an integral transform of some kind? Or?
No, so it has a very simple definition in terms of polynomials, just not very intuitive. It's literally this psi tilde of z is d, so is psi of, so psi of alpha is psi tilde of d alpha 1 minus alpha alpha bar minus delta phi alpha equals 0. So it comes from a duality between, if you want, the operator, which is a combination of, in CFT, of derivatives acting on fields, and its wave function, which is a correlation function.
Is this now for 2D, or how many dimensions is this transform? Because this looks like a two-dimensional kernel for the unit disk. But
yeah, well, this is really defined at the level of L2 functions on the disk. Yeah, so it's just 2D in that sense. Yeah.
Thanks.
So this potential you wrote down, does anything interesting happen when you set the dimension to 2? Because it looks like almost like an integrable potential.
Integral, yeah. So yes. So I mean, funny enough, in the 3-body problem, delta equals to 2 odd spin, it's integrable, exactly solvable. And Derkashov and Malyshev found this in old works from the 90s. But apart from that, it's not. So while it is, the arena of free field theory to have delta phi equals to 2, sort of like a typical phi-4 perturbative theory, it won't be integrable in the sense of quantum mechanics. Now, what is, I should note that this, in planar conformal gauge theory, you also have this EFT, but you should think of the interactions as being long range. But you can still describe the leading Hamiltonian that lifts the degeneracy, and that one is integrable. It's the classical XXX spin chain, and that was found by Koczemski in the 90s.
If we don't have any further questions, let's thank our speaker again.